while you're studying. The first part of the table is the centroid calculation, which we're about to do today. And the bottom portion is your area moment of inertia, that high value that we're going to do also. In addition, there is a table that looks like this in files. These are all in files. You need to download it because you're going to have a copy of this on the test along with the table. So the test will have 5 pages. Question 1, question 2, question 3. 4 is the table, 5 is this chart. Okay, so download it so we can start using it. This is going to come in handy when we get to area moments of inertia, which is probably Thursday. That's how quickly we're going to move. Okay? So make sure you download that. By the way, both of these should be in your testing manual, but they're also on Canvas under files. Okay? Got it? Centroids. Nothing new. Centroid center of gravity. This is a chapter that I did not even specify as a concept in statics. Of the 12 concepts, we never ever said centroid or center of gravity. Yet there's a whole chapter on it. And the reason I didn't say as a concept is because the underlying concept behind it is equivalence. Let me remind you what equivalence said back in chapter 4, which said, hey, any system of forces and moments can be reduced down to a single force, single moment. And in certain cases, which was the litmus test, I can reduce this down to a single force at a known location X. That's what equivalence said. And that's exactly what we're going to use in this chapter. Okay? So typical center of gravity problem says W1, W2, W3. These are all the weights in the system. I can reduce that by the concept of equivalence down to a single weight total by summing all these weights. And then using moments of this system equal moments of that system, I can find X bar, Y bar. So you can see, this is all in the videos. I'm going over it quickly. How many have seen this video? A couple of them. All right, the rest of you need to get with it. All right? Notice this is the moments of the original system. That's the moments of the reduced system. And I can do the same thing to find Y bar. Okay? That's the whole concept of center of gravity. That's it, in a nutshell. What is the center of gravity? Center of gravity is nothing more than the place at which everything is in perfect balance regardless of its orientation. Point about which an object is in perfect balance regardless of its orientation. Centroid is the center of the area. That's what a centroid is. Okay? So it's talking about the distribution of the area. Here's a simple example on center of gravity. I got a weight 10g, 3g, 8g. These are the distances in the y. These are the distances in the x. I'm going to say that's equivalent to 21g. 10 plus 8 plus 3 is 21g. And I need to find x bar, y bar. Well, how do you find x bar, y bar? Moments being generated by these 3 has to equal the moment generated by this, which is 21 times x bar and 21 times y bar. If you do it, you will see that in essence, what you're saying is moments divided by the total weight. The total weight is 21g. Here's the moments of the reduced system equals the moments of the original system. That's 10g times 4, 8g times 9, 3g times 20, 8.19. I'm not worried about the number specifically. And WT y bar is 21g times y bar is equal to W1, Y1, W2, Y2, W3, Y3. And that's 10g times 8, 8g times 5, and 3g times 7. Those are the y's. Giving me 6.7. That's how you calculate the center of gravity. Now, I'm sure in physics you probably saw mass instead of W. It's just a factor of G, no big deal. It's the same shit. Whether you use W or M, it really doesn't matter, because it's just a factor of G. Okay? That's fantastic if you have a particle system. When it comes to rigid body, that's a bit of a problem. That method we just did would be impossible to do. Why? Because a rigid body is a system of particles, and it's an infinite number. I can't do infinite force times distance, force times distance, force times distance. Not feasible. So for a rigid body, what do? Let's say this is the rigid body right here. What we're going to do is we're breaking it up into pieces. There is a little piece right here, which is this rectangle, which has an area dA and has a weight dW. Now, it has a thickness T, has a specific weight, which is weight per volume, which is gamma. dA is the differential element of the area of that little piece. dW is the differential weight of that little piece. And if you look, I'm going to say dW equals gamma T dA. Does that make sense? Well, check basically your units. Gamma is weight per volume. TdA, that's area times the distance. That's also volume. Volumes cancel, leaving me weight. That looks like a correct expression, because dW should equal weight. That's the differential weight of that small rectangle. Now, I need to sum all of these rectangles. So a summation leads you to a Riemann sum in calc, which in essence is an integral. So I'm going to integrate this side. Integral dW is equal to integral gamma TdA. Well, when you integrate dW, I'm going to get the total weight. That's going to be my denominator. Okay? Now, if I want to find the numerator, I have to find the moment about the x and the moment about the y. Here's the moment about the x. That's going to be y dW. If I integrate this, I'm going to integrate that. dW is gamma TdA, so mx is equal to that, which means mx times divided by w is equal to y bar. That is the expression. I can do moments about the y-axis. dmy is equal to x dW. That's the expression. Now, if you have a nice homogeneous, nice uniform rigid body, and it's got constant thickness, that means gamma and t are constants. I can yank them out of the integral. They will cancel, leaving me, in essence, the fundamental equations for centroid. X bar is equal to integral x dA over dA. Y bar is integral y dA over dA. Those are the fundamental centroid calculations or equations. That's if you have homogeneity and constant thickness. If you don't have homogeneity, then you got to leave the gamma TdA in there and do the integration. Okay? Couple of things about these two equations. So this is my centroid equations for homogeneous constant thickness. If they're not homogeneous, then it's these two equations right here. Okay? Couple of things, couple of notes. Kind of important. First note, numerator, that x dA, y dA interval. That's called the first moment of the area. First moment of the area. The denominator, that's the total surface area of the rigid body. Numerator has length raised to the third power. Why? It's x dA. dA is feet squared times x. That's going to give me feet cubed. Then I'm going to divide that by the denominator, which is feet squared. So I got feet cubed divided by feet squared, leaving me feet, or meters, or inches, or whatever units are using. Number 4. Number 4 makes sense once we do problems. Area is a scalar. So how do I assign a lever arm that's positive or negative? Well, it depends on, is this area to the left or to the right of the y-axis? Is it above or below the y-axis? If it's to the left, then I'm going to have a negative x. If it's below the x, I'm going to have a negative y. So your sign, in essence, is going to depend on where this area is in terms of the coordinate system used. All right, next. If a body has a plane of symmetry, then your centroid is going to lie on that plane. Example, I have a T-section. That is symmetric, which means that centroid has to lie on that red line someplace. Why? Because this area matches that area. This area matches that area. It is very symmetric. So I don't have to do an X bar, Y bar. I just need to do a Y bar. Because it's got to lie along that axis. That's what that statement is saying. Number 6 says, for any area that's completely, or volume, that's completely symmetric, then the centroid lies at its center. Example, I have a rectangle. It's completely symmetric, it's got to be dead center. That's what that statement is saying. If an object has uniform density and thickness, centroid will coincide with the CG. So the CG and the centroid are one in the same point if you have nice homogeneity. In other words, it's nice and evenly distributed, the area, or the mass for that matter. Okay? Now, we're down to finding the centroid of it. By the way, why the hell am I bothering with this? Well, because sigma equals MC over I in the next class. Shear stress is equal to VQ over IT in the next class. This sucker, that C, if I have a rectangle, that's going to be the distance C. From the neutral axis, or the centroid, to the top or bottom of the beam. That Q is going to have to deal with the centroid. So centroid is a very important concept that we need to be able to find, because it's going to pop up in these equations here and there when you go to the mechanics of materials or mechanics of solids. Okay? Now, there's two methods to solve. One is direct integration. You did this in calc. Ain't nothing new here. So what the hell did you do in calc? Here's what you did in calc. You said, all right, let me put some rectangles in here and do this area. Do you remember doing that? That's direct integration. So you can find x bar, y bar by simply saying integral x dA, integral y dA. And then substituting for these based on the rectangle. The dA would be base times the height of each rectangle. And then you're going to sum from 0 to wherever. That's direct integration. I'm not going to spend a whole lot of time on direct integration. Why? Well, because I can't do it. No, because in the real world, you ain't going to do a fucking integration anymore. Trust me. Unless you get some architect that's going to give you some funky ass looking thing and then you go, ah, shit, I'm going to have to do integration. What does that percentage going to be? Minimal. What you will have to do is probably what's known as the next method, the composite body method. So I'm not going to spend time on the direct integration stuff. You've done it before. Engineers usually don't integrate. I don't care what the book says. Let's be practical, okay? But you may use what's known as the composite body method. What you see there is two equations. That is the integral of x bar, y bar, but put not in integral, but in discrete form. So the integral became a summation. Okay? So xa divided by summation a. It's the same thing as me saying x bar is equal to integral x dA over integral dA. Well, in discrete form, this is the integral form. In discrete form, it's summation for the integral x for that x, and dA is a, divided by summation a. So this is the discrete form of these two that we did find before. So in discrete format, we are going to use the principle of superposition. That was one of our concepts. And it's a concept that's used not just in statics, it's going to be used in mechanics materials, it's going to be used in the electrical system, it's going to be used everywhere in engineering. What do? Well, you've actually done this before. You take a piece here and say, what's the area of this? Shit, let me break it up into pieces that I can digest and that I can see pretty easily. So I'm breaking it up into area 1, a square, a rectangle, a semicircle, and a triangle. If I add up the area of 1, 2, 3, and 4, I'm going to get the total area, right? So all I did was I superimposed a triangle, a rectangle, a semicircle, and a triangle to get to the overall area. That is, in essence, the principle of composite bodies. That's it. It's not that hard. I told you, test number 3 is not hard. I didn't lie to you. Okay? Now, if you have some sort of hole or a cutout, you're going to treat it as a negative area. Simple as that. Where am I going to get you? You'll forget the negative sign because you're not paying attention to details. Where else am I going to get you? You multiplied two numbers that shouldn't have been multiplied to get a third number. Or you just simply don't add, subtract, multiply, and divide correctly. So it's a mathematical error. Okay? You with? Okay. That said, again, these are the equations for the centroid. These are the equations for center of gravity. Where is all this coming from? Equivalence. That's why I never said, although there's a whole chapter, I never said center of gravity centroid was a concept in this class. Yet there's a whole chapter on it. Okay? Now, you will see where is it? You'll see on page 163 of the photocopy booklet, you'll see me do an integration because I don't want to leave you without having kind of given you an idea of what integration looks like. And I'm sure the book has several examples of integration. All right? And I try to be very painstakingly descriptive so that you know exactly what I was thinking since I'm not going over it with you. You'll see what I did in great detail. So if you ever have to do an integration, you have a sample of what to do. All right? All right. Let's go back and start doing some of these Page 158. Page 158. So it says, find me the centroid of this. Again, why the hell am I worried about this? Well, I'm worried about this because if you go on to the next class, you're going to have to find the centroid, whether you like it or not. Alright? So the first thing, if there is no coordinate system, put a coordinate system. Where you place that coordinate system is completely arbitrary. There's my coordinate system. So what I see is two pieces. I see a rectangle and a hole. Of course, we're going to start out with something relatively easy. So if you look, I'm saying to you, I have a rectangle to which I'm going to add, or in essence subtract, a hole to equal the original diagram. So this is my area 1. This is my area 2. Makes sense? So I'm going to separate it into two pieces, area 1, area 2. So I'm going to calculate, remember, x bar is summation xi ai over summation ai. This denominator is total area. Same thing with y bar, summation yi ai over summation ai. Well, the total area is area 1 plus area 2. That's going to be, this is 5 plus 1, 6. The base is 6. The height is 2, 4, and 4 is 8. So this is base times height for area 1. Plus area 2 is a minus pi r squared. So that's 48. Plus a negative pi times r. R in this case is half of 2, which is 1 quantity squared. Area total is equal to, and by the way, on a test, I want you to use 3.142. I don't want you to use the entire digits that your calculator gives you. So pi for me is going to be 3.142. Okay? This is going to give me a total area of, in essence, 44.86. Now, I did not keep 3 decimals. On the test, in my solution, I keep 3 decimals. Okay? I didn't keep 3 decimals. I got sloppy. But I want you to keep 3 decimals. So what did I just find here? I found the denominator of my x bar, y bar. Great. So now I know x bar is equal to area 1, y1 plus area 2, y2 divided by 44.86. And I know y bar is area 1, y1. This is x. Plus area 2, y2 over 44.86. Agreed? This is going to be area 1. Well, area 1 is 48 times its distance x1. Again, remember, this is my 1 and my y and x. Same as here. What this x1 is from the y-axis over to the center of the triangle. That is x1. From the y-axis over to the center. What value is that? Well, if you look, the base of it is 3 plus 2 plus 1, 6. So half of 6 is 3. So I know to go here, this is 3. So I'm going to write 3 here. Plus a negative pi, which is the area, times its distance from here to the center of the circle. Well, that's going to be 3 plus half of 2, which is 1, so that's going to be 4. divide this by 44.86 is equal to 2.93. Any problems on how I got my x1s, x2s from the y-axis to the center of each individual piece, the rectangle and the circle? Same thing with this one. This is going to be 48 times. This time it's the y. So I'm going to go from the x-axis up. That's my y1. Well, this whole thing is 2 plus 2 is 4 plus 8. Half of 8 is? This has to be 4. So this has to be 48 times 4 plus 3.142 times from the x-axis to the midsection. That's going to be my y2. That's going to be 2 plus half of 2, which is 1. That's going to be 3. Divide this by 44.86. Answer, 4.07. So my centroid lies at 2.93, comma 4.07. Yes, that should be a negative here. It's plus a minus, because it's a cutout. Yes, it's a negative 3.142. Now, tell me, how hard is this shit? It's not hard at all. Did I tell you that test number 3 is add, subtract, multiply, and divide? Isn't that what the fuck I just did? I multiplied these two numbers. I subtracted those, and then I divided by 44.86. This ain't hard, ladies and gentlemen. Now you can see why this test 3 is usually the highest average of all the tests. Because it's really not that hard. It's probably the easiest test in engineering you'll take. Okay? Questions on this? All right. Anything? Moving on. I'll come back to this one. I want to do this one first. Page 160. Hey, this is a symmetric animal. In other words, all I need is to find the distance along the axis, which is y. So all I need is y bar. I don't need anything else. I don't have a coordinate system. That's okay. I don't need a coordinate system. What I need is establish a datum. So I'm going to establish a datum down here. Is that datum arbitrary? Absolutely. Could I put it at the top? Yeah. I could easily put this here. Doesn't matter where I put it. I'm going to break this up into two areas. Area 1 and Area 2. Area 1 and Area 2. Well, this is easy enough. All I need to say is y bar is equal to Area 1, y1 plus Area 2, y2. Divide this by Area 1 plus Area 2, which is area total. Well, what the hell is area total? Area total is, in this case, 40 times the height of 120 plus this is base 120 times the height of 40. This is again base times height, base times height. Area total is 9600 inches squared. You don't have to convert this to feet or whatever. Use whatever units are there. It's not a big deal. What did I just find? I just found the denominator. Okay. So I know y bar is equal to 9600 times area 1. Well, area 1 I already found. It's 40 times 120 times the distance to the center of that area from the datum. So I go from here to the center. What is that distance? Well, it looks like half of 120, right? That's 60. So this is going to be 60 plus 120 times 40 times the distance from the datum to the center of that. That's 120 plus half of 40, which is 20. 120 plus 20, 140. So I'm measuring from the datum to the center. I don't need to put an XY coordinate. All I need is a Y distance. So I'll just establish a datum at the bottom. If you do this, Y bar is equal to 100 inches from the base. Now, you have to be very careful, because if you're reading the solution manual, or you look at ChatGPT, or at Chegg, or whatever, and they do a problem, they give you a number that is not 100. It's not automatically you did something wrong. The question you have to ask is, where did they measure from? Because I could have measured from the top down. Well, if I measure from the top down, what's my Y bar? It ain't going to be 100 inches. It's going to be what? What's it going to be if I measure from the top down? So here is my 100 inches from the base. What's left? Well, it looks like 20 plus 40. So from the top, it could be 60 inches. So you could get an answer from a solution or Chegg or whatever, ChatGPT, that says, hey, your Y bar is 60. The question you have to ask is 60 from where? 60 from the bottom down? Yes, it is 60. From the bottom up, it ain't 60, it's 100. You see what I'm saying? So be careful when you read solutions to make sure you're reading the right solution. They're both right. You can say 60 from the top down. You can say 100 from the bottom up. Both are completely right. Just be aware that you might get two different numbers. What?
What is that datum?
A reference point.
Okay, thank you.
Right?
I don't know how to ask.
You've never heard the word datum. Really?
This is the first question.
Damn, you guys are really, Or you clapping? Yes. I'm always looking for words. And if I don't know a word as I read an article or something, I look it up. Because I want to be educated. So, according to Webster, that is a datum. Something used as a basis for calculating or measuring the distance between datum points, making things more efficient for those of us whose work requires a time datum, whatever. But you can see it is something used as a basis for calculating or measuring. It's a reference point. So yes, and what I like about this is it gives me a word of the day. I don't know. I haven't looked at today's word, so I can't tell you what the word of the day is. Most of them are pretty obvious, but sometimes. Word of the day, laudable. Laudable. Praiseworthy, correct. How about milk toast? Huh? Nope. All right. I also see an axis of symmetry here again. Notice it's symmetric. This portion on this side matches this portion on that side. So there is an axis of symmetry here. And I'm going to put a datum, a reference where I'm measuring from, and I'm going to put the datum at the bottom. Can I put it at the top? Yes. I'm putting it at the bottom. So what I'm doing here is I'm saying to you, I'm going to break this up into 3 pieces. Piece 1, piece 2, and piece 3. Now, once it goes beyond 2 pieces, I generally put things in a nice, neat table. And that is why you have this for you to use. So once I get beyond 2, I start using the table. And I usually use this when I have more than 3 pieces. Here I have 3 pieces, not a big deal. So I'm going to say, here's my table, component, area. I don't need an X bar, I just need a Y bar. I need a Y bar times A. So the first is a rectangle 1. The second is a vertical rectangle 2. And the third is a triangle 3 that I know is a cutout. Negative, instantly. Put it in. Don't hesitate. Now I need to sum this column, because that column is my denominator. I need to sum this column, because that is my numerator. So my Y bar is summation YA over summation A. That's why I'm summing these 2 columns. Pretty simple. What's the area of this rectangle? Well, it's this base times that height. Base is 6, height is 2. Shit, that's 12. What's the area of that rectangle? Well, it looks like a base of 4 and a height of 6. That's 24. What's the area of this triangle? 1/2 base times height, minus 6. Add this up. This becomes 30. So I know I got something divided by 30. Now I just need my Y bars. Okay, what are my Y bars? Well, for the first one, I'm going from here up to halfway point. That's going to be 12 times 1, 12. From the reference point to the midsection of this rectangle is going to be 2 plus 3, 5. 5 times 24 is 120. From the midsection, or from the datum to the middle of that triangle, that's going to be 2 plus a third of 3, that's 1. That's going to be 3. This is why this table becomes important to you. Here's the triangle. Look at the triangle on this table. You will see for the triangle, from the horizontal up, h over 3. From the y-axis over to the c, which is the centroid, is b over 3. Okay, so if you want to know centroids, this table has it. So for the semicircle, from the straight edge up to the centroid, it's 4r over 3 pi. You with me? So this table will give you locations of centroids for common shapes. All right, 6 times 3 minus 18, sum this. 114. Well, 114 divided by 30 gives me 3.8 meters from the base. Is it 3.8 from the top down? No, it's not. Now, so be careful. I put the datum here, so I'm measuring from the datum from the bottom up. You could put datum here, and I'm going to datum down. Either way is the same answer, and it's correct. Oh, let me zoom out. Questions on this? Anything but? So, question number 1, test number 3. Let me borrow your testing menu. You'll see, you'll have a shape, and it will say, part A, find me the damn central. Every single time, without a doubt. Here's a sample test. For the plane area shown, find me centroid. That's what we're just doing right now. Except now in the test, you've got 1, 2, 3, 4 pieces. And I have a piece to the left, which means my X bar here is going to be negative. And I have a piece down from the y-axis, which means my y bar for this is going to be negative. That's that, hey, it's an area scalar, and you will assign a positive negative based on where it is relative to the xy coordinate system. It was in the notes. You'll see that that's, and then of course I ask you, find me the area moment, which we haven't done yet. That's the other half of your table. It's all the same shit. It doesn't change, just so you know. Here we go for the plane area shown. Find me the centroid. Well, it looks like I have one big ass triangle that I'm going to cut out a semicircle, and I'm going to cut out a triangle. So this is 3 pieces. And by the way, on your test, I usually use about 3 to 4 pieces. Yeah, I can go 5 and 6 and 7. What's the hell's the difference? If you can do 3 and 4, you can do 5 and 6. So I don't go usually beyond 4 pieces on a test. Okay? Just so you're aware. Yeah?
So like, you see how like the semicircle is on the left side?
Yep. Yep.
Cut out, would it become positive, or?
You'd have a negative X bar.
Okay.
All right, let's go back to the one I skipped. Because this one's a little more complicated. That's why I kept it to the very end. This is on page 159. Can I borrow a pencil real quick? I'm going to make this very crystal clear to you. When I first saw this, when I made it and I started to solve it, and usually what I do when I solve something, I solve it, put it away, come back to it a couple of days later, resolve it. Make sure my answers are correct, because I don't want to come into class and my answers are wrong. That would be bad. So when I did this, now don't do anything just yet. When I did this, I said, okay, I'm going to have a quarter circle. I'm going to have a big rectangle. I'm going to create another rectangle right here and cut out this semicircle, and then I have a triangle. So I looked at it as 1, 2, 3, 4, and 5. Do not ask me why I saw that, but that's what I saw when I first looked at it. I put it away, came back to it. I didn't look at my solution. I came back, and this is what I did. I said, I have this big ass rectangle, which I'm going to cut out a semicircle, and I have a triangle. So the first time I did it, I saw 5 pieces. The next time, which I didn't even look at it, I saw 4 pieces. Did it matter? The answer is no. The answer was identical. My point to you being, the person sitting next to you may see 4 pieces, may see 5 pieces, you may see 3. It's the way you spatialize things. That's what it's going to come down to. Some people see space a little different than other people. The answer is, it doesn't matter. The person next to you could do it in 5 pieces. You could do it in 4. You're going to get the same answer. Here's the difference. The difference is the person that did it in 5 is going to do more work than the person that did it in 4. That's it. That's the only difference. But again, it's how people perceive figures and space. There is no right or wrong. The only right or wrong is, did you get the same answer? If you did, then you probably did something mathematically wrong. Not because you saw 5 pieces and they saw 4. Okay? So keep that in mind, that some people will see 6 pieces. That's fine. Not a problem. Could I have brought this up in more than 4 pieces? Yeah, I did it in 5. Could I do it in 6? I could do it as many pieces as I want. Like, if I wanted to, I can come in here and say, all right, I got this, I got this, I got this. 1, 2, 3, 4, 5, 6 pieces. Does it make sense? No, but to somebody that might make sense. It's what they see. Okay? So, there is no right and wrong on how you divide this damn thing up. That's what I'm trying to get across to you. The only thing that you need to be aware of, the more pieces you put in, the more work you're going to do. That's it. So here, I'm going to go with my second, which was 4 pieces, because it's less fucking work. So there's 1. Here's 2. The cutoff is 3. That's a negative area. And this is 4. Now, I got freaking more than 2 pieces. So here's what I'm going to do. I'm bringing this table into play. Remember, the upper portion is the centroid. If you look at the table, the area, that's going to be what I sum to be my denominator. This x times a, I'm going to sum to be my numerator. So if I take that column divided by that column, I should get my x bar. If I take this column, sum it, divide by that column, I should get my y bar. And it's separated out so you can see the pieces as I build it. Okay? So here, we're going to draw it up as a quarter circle 1, a rectangle 2, half a circle 3, which I know is a cutout, so I'm going to put a negative on it right away because I don't want to fucking mess up a negative sign. You with me? So, where do you think I'm going to get you? You're going to forget the negative sign. That's number 1 error made. Number 2 error made, you're going to multiply 2 columns that shouldn't be multiplied together. Number 3, you dumped something into your calculator that wasn't correct. In other words, it's a math error. And then lastly, the triangle 4. Okay, quarter circle. Area 1 is 1/4 pi r squared. That is 1/4 pi times the quarter circle radius is 7 squared. That's gonna give me 38.5. And I should keep 3 decimal places. I will on an exam. So on an exam, please keep 3 decimals. Area 2, that's gonna be base times height. Base is this right here, which is 6. Height is 7. 6 times 7, well shit, that's 42. Area 3, that's a half a circle. 1/2 pi times r. 6 is the diameter, so half of 6 is 3. Quantity squared. That's going to give me negative 14.14. And the triangle, area 4, 1/2 base times height. That's going to be 1/2 times the base. The base is this, which is 4. The height is 7. That's going to be 14. Sum this column up. That gives me the denominator, 80.36. So I already know x bar is some number divided by 80.36. Y bar is some number divided by 80.36. That's a fact. That ain't gonna change. Now I just gotta get the numerator. Well, the numerator are these 2 columns right here. That goes here, that goes there. Okay, x bar. So I need to go from the y-axis to here. Well, if you look at that sheet for a quarter circle, notice it tells you, I'm going to blow it up so you can think. It's telling you, hey, the x bar from the straight edge over is 4/3 pi. From the straight edge up is 4/3 pi. Okay? Everybody see that? That's why this sheet becomes important for you. Okay. So, what I want is this distance. This is my G. I need that distance. But I know this distance from the straight edge is 4r, 4/7, divided by 3 pi. That's that distance. That's what I know is 4/3 pi. So to get this distance, I'm going to say x1 is 7 minus that. You see that? If this distance is 4/3 pi, this whole distance is 7, then this distance has to be 7 minus this to give me that. So in this case, I'm going to say this is 4.029. Rectangle from this y-axis over to the center of this. Well, that's going to be 7 plus half of 6, which is 3. Guess what? That's 10. Same thing for this one. It goes to here, 7 plus half of 3. It's also 10. And then I need the distance from here to the centroid of that, x4. Well, that's going to be 7 plus 6, that's 13, plus that distance right there, which is b/3. If you go to your triangle, the distance here is b/3. So that's going to be 13 plus 4/3. That's going to be 14.333. 14.333. Everybody understands the x bar. Not hard. You're going from the y-axis over to the center of the area of that piece that you're looking at. Now sum this column. Okay, well, whip out your calc. Oh no. I'm going to multiply these two. Please notice what I'm doing with my 2 fingers. This becomes important. Because you don't know how many times I've seen people multiply the two wrong columns together. This is telling me multiply this times this to get this. 155.116. That's 420. That's a minus 141.4. And these two numbers multiplied together gives me 200.662. Now I'm sum these four numbers together to get this number right here, which is 634.378. So I'm going to put 634.378 divided by the 80.36 to give me 7.89. That's how simple this is. Notice I'm adding, subtracting, multiplying, dividing. That's it. That's all I'm doing. Don't make this hard, because it ain't. What about my y bars? Well, I need to go from the x-axis up. Well, that's just 4 over 3 pi. So this is going to be 2.971. How did I get that? 4 times 7, which is r over 3 pi. What about this? I'm going to go from the x-axis up to the center. Well, that's half of 7, which is 3.5. I'm going to go from here to the quarter circle. Now, I'm going to emphasize this a little bit. This distance right here is 4r over 3 pi, based on this sucker. From the straight edge to the center is 4 over 3 pi. Do you see it? But now I have to go all the way down to the x-axis. So what I need is, in essence, that distance. Well, this distance is nothing more than 7 minus 4 times 3 divided by 3 pi. Agreed? That is going to be 5.726. So 7 minus 4r, r in this case is half of 6, 3, divided by 3 pi. Subtract that from 7, I'm going to get this y bar. For the triangle, I just need this distance right here, which is h over 3. That's 7 over 3. H is 7. Giving me 2.333. Any questions on the y bars? Anything bothering you with the y bar? We good? Okay, so now this is where the two fingers comes into play, because I want to multiply this times that. You don't know how many times I get people multiplying this times this, or this times that. That's why I put my fingers here and here, and then this hand right here is typing away on the calculator. So multiply these two numbers together, you get 114.384. Multiply these two numbers together, you get 147. Multiply these two numbers together, you get minus 80.966. Multiply these two numbers together, you get 32.662. That's nothing more than a multiplication of two numbers. Add this up to 13.08. This is 13.08 divided by 80.36, giving me 2.65. So my centroid is 7.89, comma, 2.65. What that's saying to you is, hey, along the x, it's 7.89, so it's about here, and it's above here, 2.65. That's what it's telling me. Now, is there anything hard about this? Is there anything hard about this? Was it somebody in here that texted me about looking at Jeff Henson? You texted me. I don't remember who it was. So he was looking at Jeff Henson, and Jeff Henson was finding where this shear crossed the x-axis at by doing similar triangles. So it was like this. So I believe the problem looked like this, where this thing went like this, and I told you I need to know where this distance is. So he was doing similar triangles, and I'm like, why the hell is he doing similar triangles? Can you do similar? Yes. However, we get this by saying, hey, that number, let's call this 100, divided by the slope gives me x. I didn't have to use similar triangles, but you can. You understand? How many have watched Jeff Henson? Did you come across that? He did, for some reason. And I'm like, yeah, you can do similar triangles, but do you really need similar triangles? You really don't. All you need is the y-intercept divided by the slope, which is the force of tension. Listen up before you bolt out of here. Oh, that's right. Sit your asses down. You're going to have one frame problem and a shear bending moment diagram problem. Everybody heard that? Frame problem is not going to be this long, drawn-out problem. You should be able to do it pretty quickly. It's a frame problem, not a method of joints, not a truss. It's a frame. So one of the things I need you to be able to do when you get out of here is be able to do a truss and a frame. Those are two biggies you must learn how to do before you leave here. Why? Because it's going to impact your next class. EML 3500 or EGM 3331. Just like this stuff that we're doing now is going to impact your next class. So don't take it lightly. Really try to understand it so that the next class is a little bit easier for you. I'm showing you what you need to know so that the next class you can become successful. And I'm doing frames and trusses because they're important. You need to be able to do them and do them pretty quickly and easily. That free body diagram is so crucial. You can't do a mechanics problem without doing a good free body diagram. Period. Okay? So, question number one is a simple frame, not an exam type question frame. A simple frame. At most 2 pieces, you could probably do in less. And then one shear bending moment diagram. Now remember, there's 2 ways. I give you the shear bending moment diagram until you find me the loads. Or I can give you the loads and ask you to draw the shear bending moment diagram. Obviously, I'm not going to give you something overly difficult at this stage. That's for the test question. Okay? So it should be something relatively easy. See you Thursday. Hey, Thursday I'm starting area moments of inertia.